Welcome to Chemistry with Caroline. In this video, we're going to look at the competition between substitution and elimination reactions for a primary alkyl halide. So there's two factors that go into determining whether you'll see a substitution or an elimination reaction, and that is how hindered the substrate is. So by the substrate, I mean our alkyl halide that we're starting with. So this example is a primary alkyl halide. It has one carbon atom attached to it, and then the other two things coming off of it in addition to X are hydrogen atoms. So that's about as unhindered as you can get. The other factor is the characteristics of the reagent. So is that compound basic or not? Is it a strong base or a weak base? Because many times a compound that can act as a nucleophile can also act as a base, and that's why we have this inherent competition between a substitution and an elimination reaction. So I've categorized the potential nucleophiles as either weak bases or strong bases over these arrows over here. And so we're going to first look at if we have an unhindered primary system and a weak base. A weak base is not a particularly strong base, and so for an elimination reaction, those tend to happen more with a strong base. And so with a weak base as your nucleophile, you're going to see a substitution reaction. And specifically, you're going to see an SN2 reaction, because this is an unhindered system, so there's plenty of room for a backside attack, and that avoids the presence of an unstable primary carbocation. So I'm going to say no primary carbocation. And remember that a carbocation intermediate is present in any SN1 type reaction. Now, if we had a nucleophile that was characterized as a strong base, so it would be a good base, good at plucking off protons, typically, we tend to see elimination with strong bases, but on the primary systems that are very unhindered, a strong base is also a really good nucleophile. So because it is so unhindered, you're again going to see substitution. Again, because of our primary system, that's going to be an SN2 substitution to avoid that primary carbocation, and because there's plenty of space to facilitate that. We can force an elimination reaction if we bulk up our base. So because our substrate is unhindered, we could make our base bulky. And so usually what you'd see there is like tert butoxide. So this is a tertiary carbon that's attached to the base. And so that makes the base a poor nucleophile because it's so large and sterically hindered. And so by bulking up our base, instead of undergoing a substitution reaction, we see an elimination reaction. So this would be an elimination reaction, and this would be an E2 reaction, because you have a strong base, so it can immediately pluck off a proton, and again, it also avoids that primary carbocation that is not very stable. So let's go to the next page, and we'll look at a couple mechanisms. So one crucial part of being able to solve these problems is to be able to identify a strong base versus a weak base. So I have videos on identifying strong bases and weak bases, so if you haven't gotten that down yet, go back and watch those videos after you finish up with this. But here I have a strong base. I have hydroxide, so there's an oxygen with a negative charge on it. That charge is localized on the oxygen. There's no resonance, and oxygen is a small atom. And so a strong base and a primary system here. So see, here's my carbon that is attached to my leaving group, and that carbon is going to be attacked by the nucleophile. So my hydroxide is going to behave as a nucleophile here in an SN2 type reaction. So the arrow will start at my lone pair of electrons on the oxygen. It will end at my electrophilic carbon that is attached to the leaving group. And at the same time, so as not to break the octet rule, the leaving group will leave. So this is an SN2 reaction. And I get this alcohol over here, and then my bromide has left. And so it has a negative charge. It took those electrons with it. So this is an SN2 reaction, and an example of what would happen if we had a strong base as our nucleophile on a primary unhindered system. In this example, I'm starting with the same starting material, so I have a primary alkyl halide again. And this time, again, I have a strong base, but this base is bulky. And that makes it a poor nucleophile, so this is going to force the elimination reaction. When you're doing this type of reaction, remember, for elimination, we label the alpha carbon, which is the carbon with the leaving group on it, and then the protons will come off of the next door neighbor carbons, which will be labeled beta, beta prime, beta double prime if there's more than one. And so it always is helpful to label your atoms so that you don't pull the proton off the alpha carbon, which is a common mistake in organic chemistry. So because this thing is huge and just a really poor nucleophile because it's so hindered, it's going to behave as a base, and so a lone pair on the oxygen is going to pluck the proton off of the beta carbon. These electrons will fold down to make a double bond, so my arrow ends in the middle of the bond to indicate that a double bond is being made. And then at the same time, the bromine will leave so as to not break the octet rule. And so what I get on the other side is an alkene, because this is an elimination reaction. And so just so we can keep track of things, this was my alpha carbon and this was my beta carbon. And then I have the conjugate acid of my base. So you get this alcohol here, and then bromine left. So I've got a bromide. This is an E2 reaction. It's concerted. The proton is plucked off as the leaving group leaves. A strong base is required for an E2 reaction. And on this unhindered primary system, it avoids a primary carbocation, which is very unstable. So this has been a look at substitution versus elimination reactions on a primary system. If you found this video helpful, please like, subscribe, and share with your friends, and I'll see you next time.